Hello everyone, Mr. Fawcett here with another lesson on derivatives. Today we're going to look at specifically a technique that makes finding derivatives of functions much easier than it was before. So before we had, let's go over this rule again. We said that the derivative of a function could be written as the limit as h approaches 0 of f of x plus h minus f of x all over the quantity, all over the term h. And then we had to do some manipulating to hopefully simplify out the h in the denominator so that we didn't have an indeterminate form. And that allowed us to find the limit. Now, this will work, but sometimes the algebra can get a bit messy. Today I'm going to show you a much easier technique that works for specific types of functions. So let's get into it. First thing we're going to do is talk about the derivatives of constant functions. So it says graph the function y equals 2 on the plane below, and then you have two other questions to answer. So I'd encourage you to pause the video, take a minute or two to answer questions 1 through 3, and then come back and listen to the discussion. Okay, so the function y equals 2 is just going to be a horizontal line that goes through 2 on the y-axis. And it says, what would the tangent line look at any given point on the graph? So for linear functions, the tangent line is always going to resemble what the function looks like. If I choose this point at x equals -3, the tangent line is going to be the same line as the actual function. If I choose a point over here at x equals 2, again, the tangent line is the same line as the original function. So the tangent line is the function itself. Okay, number 3, what does this mean about the derivative at any point for the function? Well, let's think about it. What is the slope of a horizontal tangent line, right? The blue tangent line, the brown tangent line, they were both horizontal. So the slope of a horizontal line is equal to 0. So if the slope of the tangent line is equal to 0, then the derivative at that point is equal to 0. So it has a value of 0. Oops. It has a value of 0. So there's one more example for constant functions, just because we generally don't just want to look at one example and try to determine a rule. It's better to look at several examples and see if the pattern is consistent between them. So work through questions 4, 5, and possibly 6. Let's see. No, just 4 and 5, and then we will look at a general rule down below. Okay, so if we graph the function y equals -4, that's going to be a horizontal line that goes through -4 on the y-axis. And again, if we pick any point on this graph, let's pick the point x equals 3, the tangent line is going to be the same as the original function. And notice that these tangent lines are all horizontal. So the derivative for any point on this function is also going to be equal to 0 because all the tangent lines have a slope of 0. So we can say they are both equal to 0. And you could put in there for every x value, but either way, that's okay. Okay, so we could keep going and we could look at hundreds of different constant functions, and we would see that they're all going to be horizontal, which means that the tangent lines are all going to be horizontal. So the derivative of a constant function is always equal to 0. Thus, if c is a real number, And let's say if f of x equals c, and this is what we had for our two functions above. We just wrote it in terms of y instead of f of x, but it means the same thing. Then f prime of x is equal to 0. And again, it doesn't matter what value we substitute in for x, our derivative is going to be 0. Another way to write this is to say, and this is notation we haven't seen before, or the derivative, so d dx of c is equal to 0. This right here, this d dx, is just known as a derivative operator. It means take the derivative of whatever is next to it. So if we take the derivative of c, which is essentially f of x, that derivative is going to be equal to 0. Okay, so again, I'm going to expose, there's other derivative notation that we'll get to, but for now, we have the 2, we have f prime, and we have d dx. Okay, let's move down to linear functions. Okay, so same thing, graph the function and then think about what the tangent lines would be for that function. And you can also look at 3 and 4 and 5 actually. So it may take you, 5 to 10 minutes. Try to work through the questions on this page, and then we'll have a discussion about what the derivatives of linear functions look like. Okay, so if we graph this function y equals 3x minus 2, our y-intercept is -2. Oops, let's put my pen on. -2. My slope is 3. I'm not going to go through how to find another point, just because that's a skill I think we all understand how to do. And my function looks something like this. So like with our constant functions, our tangent lines for any point on this graph are going to look exactly the same as our original function. It's just they don't end up being horizontal like they did for constant functions. But let's think about it. What would the slopes of the red and pink tangent lines be? Well, if they're the same line as our original function, they would have the same slope of our original function, right? They'd have the same slope of the blue line, which represents y equals 3x minus 2. So they have the same slope as our original function. Same thing could be said for the function down below. So if I have a function y equals -1/2 x, that is going to go through the origin, and I'm going to pick another point that will work. Oops, that is not a point that's going to work. Just thinking of a positive slope. 2, -1 would work here. So I get a graph that looks like that. And again, whatever point I pick on this graph, the tangent line is going to be the same as our original function, which means it's going to have the same slope as our original function. So same slope as original function. So if we're asked to find the derivative of, and we could just go, we'll go back up to the first one. If we're asked to find the derivative here, and I'm going to throw you another notation. So we could say f of x is equal to 3x minus 2. That would be another way of writing it. And then if we wanted to find the derivative, it would be f prime of x. We know that our derivative is the same here, right? It's always going to be equal to the slope of our original line, which was 3. So we could say f prime of x is equal to 3. Or if we wanted to keep it in terms of y, instead of saying f prime, we can just add a little tick mark to the y. And we could say the derivative of y is equal to 3. So both of those would be telling the same story, that the derivative of our function is equal to 3. Now generally you want to keep it in the same terms that it was given to you in. So I would say let's go with this answer, but both really mean the same thing. So down below, if we'll just keep with the y. If I have y equals negative 1/2 x, well, the slope of my original function is negative 1/2. So my derivative is equal to negative 1/2. Right? And you'll notice in these two examples, our derivative wasn't equal to 0, but it was just a number. It was just a constant term. And that's because the slopes of these functions are never changing. It doesn't matter what x is. So we're not going to have an x in our derivative function. All right, let's clear this up. We answered number 5 in our discussion, but we can put something down on paper. What do the examples above imply about derivatives of linear functions? Well, the derivative of a linear function is just going to be the slope of the original function. So the derivative of a linear function is just equal to the slope of that function. So it shouldn't be too hard to find the derivatives of constant functions as well as the derivatives of linear functions. Things will get a bit more messy when we see quadratic functions or cubic functions or other types of polynomial functions, which is what we're going to look at today. So let's get started. Let's go to the next page. Okay, I think I can squeeze everything in. Okay, so we're going to fill in the derivatives of the following nonlinear non-constant polynomials as well as functions with rational exponents. It says to raise your hand immediately when you think you've identified the pattern or rule. However, what I would do is just pause the video. So I'm giving you the functions here, and I'm going to start writing the derivatives. Now, when you see a pattern, pause the video, try to explain that pattern out loud, and then maybe finish watching and see if your pattern makes sense. And then we'll discuss at the end. So the first derivative would be f prime of x is equal to 6x minus 2. And again, I'm not going to pause myself in between problems, but you can certainly pause the video and give yourself time to think before you see the next example. Next derivative would be f prime of x equals negative 15x squared plus 4x minus 3. Next derivative would be f prime of x is equal to negative 9x squared plus 24x cubed. Next derivative would be f prime of x is equal to 2x to the negative second power minus, let's make that a little better, minus 6x to the power of negative 3. The next derivative would be f prime of x is equal to 4x to the negative 1/3 power minus 8x to the negative 3rd power. And our last one, f prime of x, make sure we see that prime, is equal to 3x to the negative 3/2 power plus 3/2 x to the negative 1/2 power. So if you haven't already, take some time to think and see if you can identify this pattern. There is one pattern that we could use to figure out all of these functions, and then we will discuss it down below. Okay, so let's take a look at this rule. Well, actually, we can just kind of discuss it before we write it down. So if we take a look at number 1, up here that I starred, the 3x squared became 6x. So what I did, I multiplied the exponent to the constant, so 2 times 3, and then I subtracted 1 from the exponent. Same thing with our middle term, right? This exponent on the x is really 1, right? So I multiplied, that's a poor 1, but I think you get the idea. So I multiplied 1 times -2, which gives me -2. If I subtract 1 from the exponent, 1 minus 1 is 0, and x to the 0 power is 1. So I don't have the x anymore. And then, of course, we know that the derivative of a constant is 0. We already talked about that up above. But just to show you why, so 3 is really equal to 3 times x to the 0 power. And if I apply this derivative rule, the derivative with respect to x of 3x to the 0 power, well, I'd multiply 0 times 3, so I'd get 0 times x to the negative first power. But that's really just equal to 0, right? Because anything times 0 is 0. And we applied this rule to each of these other, not all of them were polynomials because some of them had fractional exponents, but there were no quotient functions. So they got a little bit more complicated, but the rules stayed the same. So let's write a formal definition, or a formal definition for the power rule. So the power rule states, if n is a rational number, then the function f of x equals x to the power of n is differentiable, and f prime of x is equal to n times x to the power of n minus 1. Or we could write it using our derivative operator. So that's this d over dx, and that just means we're taking the derivative with respect to x of x to the power of n is equal to n times x to the power of n minus 1. Notice down here it says, oops, let's pull out my pen. Last thing, for f to be differentiable at x equals 0, n must be a number such that x to the power of n minus 1 is defined on an interval containing 0. And all they're saying is, with that statement, is that if we had a function like f prime, let's do the original function first. If we had a function f of x is equal to, let's say, 3x to the negative second power, if I took the derivative, I get f prime of x is equal to negative 6 times x to the negative third power, which is really equal to negative 6 over x cubed. So if we were trying to find f prime of 0, right, f prime of 0 would end up being negative 6 over 0, which is undefined. So the derivative would not exist at x equals 0 if your denominator is going to be 0. So that's all they're saying with that little clarification at the bottom. The main thing you need to focus on, though, is understanding this rule. You will use this rule constantly throughout this entire course, and it'll make more sense when we actually use functions rather than using these x's and n's and whatnot. So that'll be it for this video. When we come back, we will go through quite a few example problems on how to use the power rule, but you probably want to try those on your own first anyway before you look at the answers and explanations. Until then, this is Mr. Fawcett. Enjoy the rest of your day.